Hello, I'm Ethan Fish, and today I'll be talking to you about modeling systems. We're going to start with Module 6, which is modeling electromechanical systems. Some big high topics that we're going to talk about that you want to kind of jot down and make sure you have a good understanding is the back electromotive force, or the back EMF. Current carrying rotating coils and magnetic field have current, voltage, and force. Voltage is equal to its magnetic field strength times its length times the velocity. Force is equal to its magnetic field strength times length times its current. From these, we were able to conduct the torque equation, where a torque is equal to the torque motor constant times our current, as you can see right here, Tm. And then the back EMF equation, where we have an electromotive constant times the derivative of our angular position, which we can then write into the Laplace form that derives as an S times our angular position. Here we have a list of mechanical constants. And then later in our slides, you'll be able to see how these equations will play a role in solving for the transfer function, which you'll be able to see this is the first equation up here. Right here, this will be our resultant transfer function after a large derivation that we will not go into in this slide, or in this slideshow, but can be reviewed. So as you can see, theta m over EA will be the resultant transfer function for our basic system. This equation here, Jm is the equivalent inertia at the armature, which includes both the armature inertia and the load inertia reflected to the armature. And then this equation here is dm is the equivalent damping at the armature. And then these two equations here we talked about in the previous slide. Okay, here's an example that we will slowly work through with just variables and no numbers. Kind of get an understanding of what's going on here. So we want to find a transfer function, theta m over EA. But first we kind of want to understand our system before we dive into that. So a motor is an electromechanical component that yields a displacement output for voltage input. Then a mechanical output is generated by an electrical input. And that motor is shown over here by the rotor. We have the position of the motor given whichever voltage signal we are sending to that motor. Then the motor is connected to some kind of load, which would be here at the rotor. And also in this figure, there's a magnetic field developed by stationary permanent magnets, or stationary electromagnetic field. And then this rotating armature circuit, when current flows through this magnetic field, it will feel force from these magnets if it's coming at the right angle. And this force can be calculated as F equals B times L times IA, which is your current. And B is the magnetic field strength, and L is the length of the conductor. Okay, now to solve for this, we'll apply KVL through the armature circuit here. As you can see right here, we're solving for that using KVL. And then we also have the back EMF equation for VB related to our theta m term. So we can get rid of our current in that equation using our torque equation for the motor. Now we've got EA, Tm, and theta m in our equation. We just want theta m and EA. In order to get Tm, we need to take our mechanical system, where we have our motor and our load, and create an equivalent system shown on the bottom of the slide here. Excuse me. Be right here. As you can see, the motor torque is happening at the motor, so we need to reflect that load onto the shaft of the motor using You get an equivalent system. After some simplifications, the transfer function obtained is shown here in the bottom right corner. Our mechanical model is needed now. Everything reflected to the motor shaft. So we take our equations, we plug them into the equation for the armature circuit, and then when that is solved, we will be able to simplify that into our transfer function. So what does this really mean? Once the load is reflected on the motor shaft, we get a lot of different constants in the transfer function. No matter what the system looks like, we will solve for equivalent inertia and friction coefficient. Anything that is moved in the system is equated by destination divided by source squared. So if we go jump back a slide, let's do that. But we saw we had N1 over N2 in a couple of those equations. That's moving, that's a gear ratio, so it's moving that load from down here. Say it's got some kind of load here, and it wants to go, we need to bring it up to here to make it equivalent. So we'll take this N2, N1, and we'll theoretically bring all of this up here and solve that way, which makes it easier in our calculations. Now on to electrical constants. Looking at the first equation here, you're able to determine, you'll be able to make a torque speed curve. And this helps us understand different electrical components or constants and where they come from. This here is torque speed curve. The torque axis occurs when the angular velocity reaches 0. The value of torque is called the stall torque. Angular velocity occurring when this torque is 0 is called the no load speed. The electrical constants of the motor transfer function are found in two equations, and those two equations are these right here. To get to electrical form from mechanical, you'll take the angular position and change that to angular velocity. Assuming you'll be looking at a constant voltage, so that EA term is going to be constant, then the torque speed curve arises. The easiest to calculate is the no load speed, which is the maximum speed, therefore a specific voltage. At looking at what happens, there is when there is 0 speed. We have stalled the motor, and that is where electrical constants are equated from. Now we'll get into an example with numbers, and you'll actually see where all these equations come into play. For example, here is motor whose torque speed characteristics are shown in figure 1, which is the figure at the bottom of the slide here, drives the load shown in the diagram. Some of the gears have inertia, and hence inertias add for any gears connected via a shaft. We need to find the transfer function theta 2s over EA of s. Here's our system. And then, as you saw earlier, this is the basic transfer function that we want to equate to. From the torque speed curve, we are able to determine our KT over RA, which equals T stall over EA. And our constant here, which will equate out to 1/4. And then we're moving all the inertia and dampers to the motor. So this is where that destination over the source comes into play. You want to move all of that up to that top line. So we take this information and we plug that into our first transfer function here. And we want theta 2 over EA. So we're going to use our gear relation, and this is what it equates to. Thank you.